Why is the night sky dark? It sounds obvious at first because the sun is on the other side of Earth at night, right? But that's not the real question. If the universe is infinite, eternal, and uniformly filled with stars, then every line of sight in any direction should eventually hit a star. The whole sky should be blazing, as bright as the surface of the sun, in every direction, always. Yet when you walk outside at night, it's mostly darkness punched by a few points of light. That impossible contrast is Olbers' paradox, and it rattled astronomers for centuries. Heinrich Wilhelm Olbers wrote about it in 1823, but the problem was recognized earlier by Johannes Kepler and Edmund Halley. They tried to fix it with common-sense answers, and each one broke under closer inspection. Stars being far away doesn't help, because while individual stars get dimmer with distance, the number of stars increases with distance too. The inverse square law for brightness and the cube of volume cancel in an infinite universe, so every shell of space contributes the same total light. Stack infinite shells, and you get infinite light. Dust-absorbing starlight doesn't save the day either. In an eternal universe, dust would heat up, reach thermal equilibrium, and glow as brightly as the stars themselves. Even stars blocking stars still leaves you staring at star surfaces in every direction. In a truly infinite, eternal, static universe, the sky should be a uniform blaze. So why isn't it? The real solution is a combo punch from modern cosmology. First, the universe has a finite age, about 13.8 billion years. Because light travels at a finite speed, we can only see within our observable universe, which is about 46 billion light-years in radius when you account for cosmic expansion. Most lines of sight don't actually intersect a star before they hit that horizon where light hasn't had time to reach us. Second, the universe is expanding, and that expansion stretches light. Distant starlight is redshifted into longer wavelengths, often out of the visible range and into infrared or radio. Even when light does reach us, expansion can dim and shift it beyond what our eyes can detect. Third, stars haven't always existed. The first stars didn't form until roughly 100 to 200 million years after the Big Bang, so there hasn't been infinite time for starlight to build up. Put those three facts together: finite age, cosmic expansion, and finite star lifetimes, and the paradox dissolves. Mid-video checkpoint time. Drop a comment and tell me which piece of the solution surprised you most. Was it the 46 billion light-year observable horizon? The idea that expansion redshifts light out of visibility, or that stars only started shining after the universe cooled enough? I want to read your take and spark a real conversation about what darkness actually means. Back to the story, Olbers' paradox wasn't just a neat riddle, it was a clue that the universe couldn't be static and eternal. It helped nudge science toward the Big Bang idea long before Edwin Hubble's discovery of cosmic expansion, showing how a simple question could expose a flaw in our assumptions. The night sky's darkness is not an emptiness, it's evidence. It tells us the cosmos had a beginning, that the fabric of space is stretching, and that starlight has limits. If you love this kind of mind-bending science and nature content, hit subscribe for more cosmic paradoxes brought to life with energy and clarity. Now imagine an alternate universe where Olbers' paradox went the other way, where the sky blazed non-stop, day and night, and individual stars were buried in uniform brilliance. Would humanity have ever developed astronomy without constellations and deep darkness to inspire us? Would we even guess that galaxies existed? Our dark sky is a gift. It lets us see stars, measure distances, and read cosmic history written in light and shadow. The next time you look up, remember that the darkness itself is telling a story. What else in our universe looks simple but secretly rewrites the rules of reality?